Testing. Okay, class. Today we're going to be reviewing equations of straight lines. For some of you, you're very familiar with this if you have a strong algebra background. Others maybe not as much. I'd like to begin by making a chart to graph these points. So I have two equations here. So I'm going to start with the top one. If I were to make a chart, we'd be looking at an XY chart, something like that. I can choose values for X, which we frequently call our independent variable. So I'm going to pick a value for X. For example, I'm going to choose 0. If X is 0, I would have 3 times 0 plus 2 times Y equal to 12. That would be 0 plus 2Y equal to 12. Dividing by 2, I would get Y to be 6. I probably won't show this procedure on the next few examples, but this is what would occur. So if I were to let, in the next case, let Y be 0, that would make this 2 times Y to be 2 times 0. It would drop out. And all I would have left is 3x equal to 12. X would then have to be 4. Another point I could choose for X, some make it easier than others, but if I were to let X be 2, that will make it easier because 3 times 2 here would be 6, and I bring the 6 over, it would be a negative. So I would be left with 2y equal to 6, and y would have to be 3. All of these points happen to be nice integers. However, sometimes it won't be a nice integer. If, for example, I had chosen the point 1 for X, I would have had 3 times 1 plus 2y equals 12. That would have given me 3 plus 2y to equal 12. Bring the 3 over, it would leave 9. Y would be 9 halves, a fraction. And that can happen. As you do more of these, you would get more skilled at choosing integers for X or for Y so that the result would also produce an integer. I'm looking to graph these now. I've chosen 4 ordered pairs here. Really, it's wise maybe just to choose 3. But if you were to look at these, it would look like the following. I have the first ordered pair 0, 6. The next one is 4, 0. Those two are typically called the intercepts, this one being the y-intercept where it crosses the y-axis. This point is known as the x-intercept where it crosses the x-axis. 2, 3 is going to be approximately right about there. And 1, 9 halves, that's 1, 4 1/2, would be right about there. Notice all these points lie in a line. So I can graph that equation. It makes a line. One of the more important concepts to remember in this setting is that this line is made up of an infinite amount of points. Every one of those points would have coordinates similar to these in the chart. Every one of those points has coordinates that make that equation true, which means every one of these points are solutions to that equation. we couldn't possibly give all of these infinite solutions in a chart like this because we would be writing that chart out forever. But what we can do is just graph the line, which basically covers all the points that are, in fact, solutions to that equation. Next, I'm going to look at graphing the second equation. I can choose different values for x here. An easy one is, of course, let x be 0, because that means -2 times 0 drops out, and I'm left with just y equal to 5. So the y has to be a value of 5. Other values I could choose would be x equal to 1. Then -2 times 1 would be a -2, plus 5 would be 3. I could also, in this case, choose x to be 2. A -2 times 2 is a -4, plus 5 would be 1. I have 3 points. That would be enough. Obviously, 2 would make a line, but the third point is kind of a checkpoint. So 0, 5 is my y-intercept. 1, 3 would be the next point, would be right here, and 2, 1 would be this point. They all lie in a line, which increases the probability that I've done these correctly because they're supposed to lie on a line. Again, all the points on this line, infinite amount of them, would have coordinates that would work in this chart to make that equation true. But now, an important concept. Look at the y-intercept of this line. The y-intercept is where it crosses the y-axis. This y-intercept is 5 because it's 5 units up. Notice on the original that 5 is showing right here as the number being added by itself. Also notice that my slope goes down 2 over 1 every time. This line, if I were to extend it, would be down 2 over 1 every time. Down 2 over 1, down 2 over 1. That down 2 over 1 is our slope, which we looked at in the last section. That slope would be a -2 over 1, or we would simply say a -2. Notice that that slope also is in my original equation. So in that original equation that time, my y-intercept was 5. The number in front of the x, -2, was my slope. That was not true over here with this one. It was true in our second equation. And the reason it's true in the second equation is because the second equation is solved for y. When we solve our equation for y, the number in front of the x is your slope, like it was down 2 over 1. Because it's the slope, we'll give it our letter for slope, m. Then I have taken times x, and then I have some number that's either added or subtracted, depending on the sign of the number. That number, you recall, was our y-intercept. We give a letter for that. We just call it b. B standing for y-intercept. So my slope is the number in front of x. My y-intercept is the number by itself. This is only when you solve for y. Very, very important. Only when you solve for y is it in our slope intercept form. So we'll list it as a slope-intercept form, y equal to mx plus b, where m is the slope and b is the y-intercept. Using that, then, we're just going to practice graphing a bunch of these equations. So I'm going to start off with this one. Notice that it is solved for y. That basically means it's in the form y equals mx plus b. In this example, my slope is 3. My y-intercept b is a -5. To graph it then, which is what we're looking to do, I'm going to first locate the y-intercept. That y-intercept is at a -5, which means 5 units down. My slope was 3, which really implies 3 over 1, which means I'm going to go up 1, 2, 3 over 1. I'm going to go up 1, 2, 3 over 1. I could continue to do that, and that would give me my line. When it's in the slope-intercept form, graphing the line really becomes very, very easy. And you can do it usually pretty fast. For example, I'll do this one a little bit faster. I first locate the y-intercept, -1. My slope is a positive 2/5. Means I have to go up 1, 2, and I need to go over 5. So up 1, 2, over 1, 2, 3, 4, 5, and I basically have my 2 points, which would work for my line. This one, graphing again a little faster. Y-intercept -3, slope down 1 over 2, down 1 over 2, I have my line. This one here, there's an important thing that I must do first. Remember, the y-intercept form means it was solved for y, like these first 3 were all solved for y. This one is not. So the first step that I would have to do is to get the y by itself. That means I would begin by subtracting 4x from both sides. That would leave me a -2y. We usually put the x term first, then the number at the end. Next, I'm going to divide by a -2. So if I divide all the parts by a -2, the reason I chose that is these -2's would cancel, giving me the y, which is what I was after, getting y by itself. -4 over a -2 is a +2. 12 divided by a -2 is a -6. I took this equation, solved it for y, so that it's in the slope-intercept form. Now I can graph it very quickly. The y-intercept, -6. Slope is up 2 over 1, up 2 over 1, up 2 over 1, up 2 over 1, and there's my line. Same concept here. I need to solve it for y. I'm going to bring the 3x over. It would be a negative. I would divide by 2. I would have a -3 divided by 2, and I would have 5 divided by 2. This time my y-intercept is a fraction. It's a little bit more difficult to graph, but not impossible. So if I look to graph this now, five halves is the same thing as 2.5. So 5/2 would be 2.5 up. My slope is down 3 over 2. So I'm going to go down 1, 2, 3 over 1, 2. And there's my graph of the line. Sometimes they will simply give us details like this problem. Give the equation of a line whose slope is 5 and whose y-intercept is 3. This is really kind of a give me problem if you are very comfortable and familiar with that slope-intercept form. That slope-intercept form was y equals mx plus b again. All we have to do is substitute 3 in for the y-intercept b and substitute 5 in for the slope m. So my answer, giving the equation would be 5x plus 3. And that's all I would have to do with that one. This one, give an equation whose slope is 0 and whose y-intercept is 4. Well, that slope-intercept form again is this. My slope turns out to be 0. My y-intercept is at plus 4. 0x is going to drop out, and that's why we end up with y to be 4, just y equal to some number. Again, if you were asked to graph that, the y-intercept was 4. The slope is 0. You can imagine it as 0 over 1, which means I would go up or down 0 and just over 1, giving me again that horizontal line. We'll talk more about that in a few moments. Next, we would like to introduce some different forms besides just the slope-intercept form. The general form, which they might ask you to put your answer as, means I'm going to take the x term first, followed by the y term, equal to a number, whatever number is left. So here's an example. Negative 3x, that's my x term. The y term happened to be, in this example, 4y. The number is 9. If you're asked to put a problem in that slope-intercept, the general form, let's, for example, just take a problem like this, y equal to 3x plus 4. That was equal, or that is in the slope-intercept form. If they wanted me to take this equation and put it in the general form, I would move the 3x over. Then I have my y term, which is just a 1y. And then I have the number, which is my c. So here I took a slope-intercept form and put it into general form. Pretty easy process, just x term first, then y term, and then c. The only time this could be a little bit of a challenge would be if I had something like this, y equal to 3/4 x plus, let's just say 1/5. One of the things that's implied in this general form is that a is an integer, not a fraction. B is an integer, not a fraction, and C is an integer, not a fraction. So if I take this 3/4 x term and bring it over, it would be a negative 3/4 x. Then my y term, which is y, equal to my number, which is 1/5. This looks like it's in general form. I have my x term first, then my y, then my number. But these aren't all integers. This is a fraction. The 1 is an integer, but 1/5 is a fraction. So I would need to change these into all integers, and I would do that by taking the entire equation times the common denominator of 4, 1, and 5. The common denominator would be 20. 4 would cancel into 20 5 times. 5 times a -3 would be a -15x. 1 would not cancel into 20, so I would have 20 times y. 5 would cancel into 24 times, and 4 times 1 would be 4. Notice now that answer is in ax plus by equal to c form, and I have all integers. I don't have any fractions. That would be a procedure to go from an equation with fractions into general form. The slope-intercept form we've just got done working with, so I'm not going to spend a lot of time right now with that. That's that y equals mx plus b. Here is just a made-up example. Y equals 4/5 x minus 6. The minus 6 is our y-intercept. 4/5 is our slope. Here's one that maybe is not as familiar. Point-slope form. The reason we call it point-slope form is it's a form that displays a point on the line, and it's a form that displays the slope. For example, right here, m is my slope again, and my point that's on the line has x1 as a coordinate and y1 as a coordinate. So these two coordinates are going to be a point that's on the line. For example, over here, a point that's on the line would be 5, 3. Notice x1 had a negative in front like this one did, so the point is actually 5 for the x. The y1 had a negative in front, just like the 3 did, so the y1 would have been a 3. This point, 5, 3, is on that line. Also, its slope is the 4. That's the number out in front. This is a form that we can get an equation of a line easy if I know a slope and a point that the line goes through. Let's take some examples now that would do just that. Find an equation of a line with slope 3, y-intercept 5, and then put our answer in general form. Well, this one is typically probably considered one of the easier ones because we gave you the y-intercept and we gave you the slope. Because I have y-intercept and I have slope, it is screaming at me, use the slope-intercept form. So that slope-intercept form was y equals mx plus b. I can put my slope 3 in. The y-intercept is 5. That is an answer, but they wanted me to put the answer in general form. General form, you remember, is ax plus by is equal to c. They want the x term first. So I'll put that x term over here, negative 3x. Then my y term, which was 1y, equal to my number 5. This could be an answer for the equation of this line in general form. Sometimes your book may take the whole thing times a -1, or take both sides times a -1. That would make this a positive 3x. That would make this a negative y. It would make this a negative 5. I switched the sign of everything. It's the same equation. It would also be a correct answer. We would accept either one of these as a general form because they have the x term, then the y term, then the constant, and there's no fractions. Let's take a look at this one next. Notice they gave me the slope, and they're telling me that it goes through some point. Well, that is screaming at me again from our previous slide, this point slope form, or that equation right there. That's the one that I should be using. So I'm going to begin with that. That was y minus y sub 1 is equal to my slope times x minus x sub 1. My slope then goes right in for the m. So I have a 3 here. This is just my general x variable. That y is my general y variable. But now x sub 1 is the x coordinate of a point on the line, which in this case is that 2 from right over here. So x sub 1 and y sub 1 are right over there. So x sub 1 is the 2, which means I'm going to have minus the 2. Y sub 1 is the 5, which means I'm going to have minus 5. It did not tell me in the problem to put my answer in general form or slope-intercept form. It just said write an equation. I could be done right here. If they had asked for slope-intercept form, then I would have needed to solve it for y. I would have had 3 times x. This would have been a negative 6. When I brought the 5 across, it would have been positive, leaving me a negative 1. This equation is equal to that equation. It doesn't look that much the same, but it actually is the same equation. That would be slope-intercept form. If they had wanted it in general form, I would have brought the x across, then plus y equal to a negative 1. They're all integers. That's another answer. All 3 of these would work. If they didn't specifically identify which type they wanted, I would have stuck with the top one, because it just means less chance of error when I'm altering the form. This one is a little more challenging yet. They want the equation of a line. They tell me that it goes through these 2 points. The previous ones always gave me a slope of 3. Way up here was a slope of 3. There's no slope given here. That means I'm going to have to find the slope first. I can do that. You remember previously in our previous lesson, we had a formula for the slope. It was the difference of the y coordinates divided by the difference of the x coordinates. That came from our previous lesson. Y sub 2 is the second y, over here the 1. Minus y sub 1 is the first y, that being the 6. The second x takes me back to this point. The second x is the 3. The first x is the negative 2. So I end up with a negative 5 over 3 plus 2, or 5. My slope turns out to be a negative 1. So my first step for this problem was to find the slope. If one of these were a y-intercept, I could use the slope-intercept form like I did on my first example. But neither one of these is where it crosses the y-axis. But I do know that both of these represent a point on the line, just like up here, this point was on the line. I can choose either one of these as a point on the line and then use that point slope form. So going to that point slope form, like we did in the second example here, it was y minus y1 is equal to m times x minus x1. Putting my slope in, which we just found over here to be a negative 1, Now I have to decide which one of these points I'm going to put in for x1 and y1. Technically, I can take either one. I will end up getting the same answer. Because I like positive numbers to work with and they're small, I'm going to go with this one. The y is a 1. So that y1 will be that 1 value minus x sub 1, which is going to be a 3. I could have taken that same formula and I could have used this point. It would have been y minus 6, my slope again a negative 1, times x minus a negative 2, using that point. I realize these don't look like they're the same, but let's show in fact that they are. Let's put these both now in general form. That means this negative 1x would be brought across, making it a positive. This y would be the next. And then I need my number out here. I have negative 1 times negative 3, which is a positive 3. When I bring that 1 over, it'll be a positive, which gives me a 4. If I were to do that here, this negative x would be brought over, making it a positive x. Then my y term. I have this time a negative 1 times a positive 2, which would be a negative 2. When I bring this negative 6 over, it would become a positive 6. Positive 6 minus 2 is 4. Notice these are the same. They're both in general form. Basically, that was to show that I could have used either one of these 2 points for my x1 and my y1. We'd like now to take another look at horizontal and vertical lines. We've done some work with that. A horizontal line, obviously one that goes straight across from left to right, it does not rise or fall. It does not go up 2 over 1 or down 3 over 2. It goes up or down 0 every time. We say they rise 0 and they fall 0, which means their slope had to be 0 or m was 0. Because m is 0, if you look at the slope-intercept form, when the m is 0, it means 0 times x is 0, and that 0x drops out, and that's why you just get y equal to the y-intercept. Here was an example, y equal to 3. 3 had to be our y-intercept, which means my line went through the point 3, or 0, 3, the y-intercept, and it's a horizontal line, so y equal to 3 would be that line. Vertical lines rise and fall, but they move to the right 0 units. Because they move to the right 0 units, my slope, which is rise over run, it might have risen some amount. I'll make up a number here, just say 4, but it did not run to the right or left, which meant I was dividing by 0. That means that I have no solution for the slope, or we say there's no slope in that situation. We're dividing by 0, hence our slope is undefined, or we say they have no slope. Those lines are in the form x equal to a number. So if I have x equal to some number, it's going to be a vertical line in this case, x equals 3. So it's a vertical line that goes through all the values where x is equal to 3. One thing to notice is all these points right here, let's just take this one, would be 3, 1. This one up here would be 3, 3. Up here would be a point 5, 3. There would be one down here at, 3, 5. I did that one incorrectly, I apologize, 3, 5. This one would be at 3, negative 2. I know they're kind of small, but notice every time the x was a 3. That's what makes the line a vertical line. And that's what this is saying. It doesn't matter what the y's were, the x was 3 every time. To make sure we get that then, if I have x equal to a negative 2, if I wanted to graph that, it would be a vertical line going through a negative 2. Okay? The next concept that we're going to look at here is the idea of parallel slopes. It produces what is known as parallel lines. When lines are parallel, for example, we might say something like these two. I know I didn't draw this perfect, but those are approximately parallel lines. That means they have the same rise over run for each of them. Or we would say they have the same rise over run, same vertical change over horizontal change. We would say they have the same slope. Parallel lines, same slope. For example, notice these right here. I have a point on the grid right there and a point on the grid right there. I went up 1, 2, 3. And I went over 1 unit. Notice this one also went up 3 and over 1 unit. Both of these have a slope of up 3 over 1 or simply 3. Most important, both of them have the same slope. Problems that we encounter with that is we'll be looking at finding an equation of a line again, but they're saying it's parallel to this line and it goes through this point. This point is not a y-intercept, so that's kind of telling me to use that point slope form, which we've used earlier today, which is that form. Obviously, the negative 4 would go in for the x, the 7 would go in for this y. But the slope is not given to me. All it does tell me is that it's parallel to this equation. That means it has the same slope as this equation. Knowing that it has the same slope, I need to get the slope from that equation. I could make a chart and graph a bunch of points. That would work, but it would take more time than another method. A better method would be to solve this equation for y, because then I know if it's solved for y, the number in front of x would be my slope. So I bring this 3x over, and if I do that, I've got 2y equal to a negative 3x plus 12. Then I need to get the y by itself, so I'm going to divide by 2. If I divide everything by 2, I get the y by itself, I get a negative 3/2 plus 6. That negative 3/2 is my slope because it's parallel to that line, and that line has a slope of a negative 3/2. So that slope I can put over here now into my formula. Negative 3/2. Now I just have to take this point and plug it in for the x1 and the y1. So the x is a negative 4, so that has to be put in here. The y1 is a 7, so that has to be put in there. They would probably expect me to cancel that double negative, but I could leave my answer right in this form now. It didn't tell me which form I needed to put it in, and I could leave it just like that. This one is a little bit easier for us. They again tell us it's parallel to this line. Just like here, they said parallel to that line. They gave me a point that it goes through. Just like here, they gave me a point that it goes through. This one's easier because I can get my slope right here, the number in front of the x. So because it's solved for y, the number in front of the x is my slope. So this one goes a little faster. Y minus y1 equals m times x minus x1. I'm going to put my slope in, 4. My x coordinate is 2. My y coordinate is 5, and I would be done. A little bit more difficult answer for us, or difficult concept for us, excuse me, is the concept of perpendicular lines, or we might say perpendicular slopes. This isn't quite as easy as what we just got done with, parallel slopes. Perpendicular lines form right angles. That means their slopes form right angles. So now take a look once at these two lines. They form a right angle right here. I know this is too small, but that one gives me a slope right there because it's an equation solved for y. So that number right there is the slope of the red line. This blue equation, again, I know it's too small for you to read, but the number in front of the x is the slope. The slope for the red line was a negative 3/5. That's actually what's right here. The slope for the blue line is 5/3. We have similar integers here, but we have one other change, and that is one slope is negative, the other slope is positive. Perpendicular slopes will always have one negative slope, one positive slope, unless one of the slopes are 0. But as long as neither slope is 0, one of these two slopes has to be a negative, the other has to be a positive. The other thing you'll notice is we've taken the reciprocal of them. Reciprocal means to interchange the denominator and the numerator. The 5 here is the numerator, here the 5 is the denominator. Here the 3 is the denominator, here the 3, except for the negative, has been the numerator. When we have that, we call them negative reciprocals. So what does that mean? It means perpendicular slopes are negative reciprocals of each other. So that would mean if one slope is, say, 7/11, the perpendicular slope, that's just a symbol I'm going to use for perpendicular slope, will be the negative reciprocal. Reciprocal means to switch them around, and then I have to make one of them negative. If, for example, my slope was a negative 4/5, the perpendicular slope I would take the reciprocal, 5/4. This one was negative, which means the negative of that would be a positive. So one negative slope, one positive. If my slope was a -3, what would be its perpendicular slope? Well, this is implied, even though it's not written, to be over 1. So the perpendicular slope would be a positive 1/3. Hopefully that's fairly easy for you to see where that's coming from. If m is 3/4, then the perpendicular slope would be a -4/3. My slope is a -5/2. The perpendicular slope would be then what? Well, we would say it's the opposite reciprocal, or 2/5. The slope is 3. The perpendicular slope is a -1/3. The slope is 1/4. The perpendicular slope is a -4. Here's the one that's a little tougher. This will take us back to what we covered earlier. This one was, if you remember, a horizontal line. And it was on a horizontal line, excuse me, y equal to some number. I'm going to make up the number in this case, just say a 3. But the slope was 0 for a horizontal line. The perpendicular slope would be the slope of a vertical line. And if you remember 10 minutes ago we said the slope of a vertical line had no slope or undefined. So the negative reciprocal of 0 in this case will turn out to be undefined or no slope at all. Okay? And finally, we have just a few problems left. 3 of them to be specific. Find the equation of the line perpendicular to that one, and it goes through some point. Okay, well, first of all, some point means I need to use that point slope form, which we did earlier, but I need my slope. To get my slope, it has to be perpendicular to this slope. I need to solve this equation for y. Because if it's solved for y, I can get the slope of that equation. So if I did solve that equation for y, it would turn out to be a -3/2 x plus 6. Slope being a -3/2. But I wanted it to be perpendicular. So I need the perpendicular slope, which would be a positive 2/3. That's the number that I'm going to put over here, a positive 2/3. Then I plug in my point. The y is a 7. The x is a -4. Take care of the double negative. And that is one form of my answer. This one would have been exactly the same, but a little bit easier in the sense that it's already solved for y. So my slope for that one was 4. The perpendicular slope, the one that I need because they want it to be perpendicular, the perpendicular slope would be a -1/4. So I go back to my point slope form. And I plug in my y coordinate 5. My slope, because it was perpendicular, has to be this -1/4. And I have x minus 2. And that would be my answer there. This one is a straight answer. Give the equation of the line or lines perpendicular to x equal to 4. X equal to 4 was a vertical line. X equal to 4 was a vertical line. That would mean that it was 4 units to the right. That would be my line for x equal to 4. I want the lines perpendicular. Well, they're all horizontal lines. There could be all kinds of horizontal lines here. We have to give an equation of those. They're all going to be y equal to some number. So I'm going to list that some number as n for any number. It could be a fraction, could be a decimal, could be an integer, but y equal to a number where n is equal to any real number. Those sometimes are so easy that they're hard. That is our assignment or our lesson for the day. I am going to be assigning section 7.2 and 7.3. This will be due 2 class periods from now. I would like you to take a picture of each one separately, and I'll have separate drop boxes for 7.2 as well as another box for 7.3. That should be self-explanatory. So we will see you next time. Have a good day.